do it. Okay. Hey, that's your line. Hello. So for this next segment, I'm going to be talking. Yeah, I'm Ryan. I'm not Corey anymore, as you can see. I have a beard. He also has a beard, but it's a different beard. And I'm balding. He has luscious hair. We're different people. Hey man, take the compliment. And we're gonna just move on to sets and selections, and I'm gonna figure out how to work this stream deck. So I apologize if there's a little bit of a hump. So there we go. You don't need me for a second. Cool. Okay, so sets and selections. Perfect. Okay. So we are going to talk about sets. It's in the title, so that makes a lot of sense. So a set is an unordered collection. Let's just, yeah, okay. So a set's an unordered collection of objects and without repeats. That's sort of the important thing here, is that we don't care about the order and we don't care about, and we don't really allow repetition. So let's just talk about some sets. Let's look at some examples. So we like to use curly braces to denote a set. So here's one. We have the set containing 1, 2, and 3. And as I was saying, that order doesn't really matter. So this is the same as 2, 3, 1, for instance. We don't always talk about numbers. Set is just objects, so you could even have, say, Van, Corey, Ryan, Anna. That's also a set. Wonderful. And let's see, are there any other ones that matter? Yes, we have this one in particular. We call it the empty set. We denote it with this circle with a slash through it. It is the set containing nothing. It is unique. And let's see, anything else? Yeah, let's talk about one more set. We have, let me see, is that right there? I can use more board space. We also have the natural numbers. We like to do this blackboard N. This is another way to write this. 1, 2, 3, 4, all of your counting numbers. And just to make some people mad, I did not include 0. That's for you. And so, yeah, here's some sets, but we are counting. So what are we supposed to do here? Ah, yes, we talk about the cardinality of a set. So the cardinality is just another way of saying the size. So how many things are in your set? So we have a few right here. Let's think about what our cardinality would be. And to denote cardinality, we just use these bars. I guess since these are the same sets, I'll just add a bar to both of them. We see there are 1, 2, 3 objects in both of these. So cardinality is 3. Similarly, yeah, we just count, hey, how many things there are, we get our cardinality. Here there's 4. The empty set, what do we think the cardinality of the empty set is?
Pi.
Perfect. No. It is 0. Perfect. There's nothing there. And then cardinality of the natural numbers. It is infinitely many numbers, so I guess I should make sure to keep consistency. It is infinite. Which infinite? Don't matter. But let's see, anything else to point out there? No. Last thing I want to really bring up about sets before we get into some more problems is this notion of a subset. Let's see, sort of just using all this space. Goodbye, sir. I'm just gonna have at all this. So subset is sort of how it sounds. It is a set that is contained in another set. So we had 1, 2, 3. That is contained. We use this sort of circle less than or equal to looking kind of thing. This is contained in the natural numbers. It is a subset of it because this is just 1, 2, 3, everything else. So the first 3 numbers are definitely in there. I think we can just go on to the next example. So we're talking about subsets and we're talking about cardinality. What I'm curious now about is how many subsets we have. We're counting now. So this theorem states that an n element set has 2 to the n different subsets. So how are we going to figure this one out? Now, let's sort of just look at 1, 2, 3 here. How could we build up some subsets of 1, 2, and 3? I mean, honestly, let's just write out what those are. So the subsets of this fella right here, we got 1 by itself. Let's just do that. There we go. We have 1. We have 2. Not doing this in any particular order. There's also the set containing 3. 1, 2. Also, I like to order the elements when I'm writing the set. Again, doesn't matter. So just to ruin my whole thing, let's do 3, 1. Perfect. 2, 3. We got 1, 2, 3, 4, 5, 6. 1, 2, 3. And now there's one thing I didn't mention before with this empty set is that the empty set is a subset of all sets. It's the absence of elements, but it is, we say this word vacuously, a subset here. I'm not going to get into the weeds about that. Trust me, it's in there. It is a subset of this feller. And let's see, we had 1, 2, 3 elements in 1, 2, 3. So this is 3 elements. And how many subsets did we get? We got 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 3 subsets. Thankfully, I didn't lie. Okay, so now how can we show this in general? What is the process with building a subset? Well, it's actually kind of nice. We sort of just, for every element in our set, we just ask ourselves, am I going to put this in my subset? So, for instance, this set 1, I just asked, hey, do I put 1 in there? Yes. Do I put 2 in there? No. Do I put 3 in there? No. Or the empty set? The answer is no every time. At every point, I had 2 options. I can either add the element or not. Let's write that down. Also, I write sort of big sometimes, so excuse me if I erase a lot. Let's actually prove this guy. So, as I was saying, we're sort of just doing a counting problem. We're saying, let's see, we have, let's just, for gigs, let's talk about the set 1 up to n. It doesn't actually matter what labels we put for our elements in our set, so long as they're just distinct. So I'm just going to think about 1 up to n here, and we can ask ourselves, this is the same question over and over again. And it's sort of phrase, is 1 in my subset? Yes or no? We have 2 options there. Is 2 in my subset? Again, just 2 choices. We get all the way up to n, and once we again, it's yes or no. Using the product principle here, we end up with 2 to the n subsets. Perfect. Oh, and take it off. Okay, so now what can we do here? Now, Corey was alluding to this earlier. There is this this fella. We have the binomial coefficient. There we go. Turn my camera off for a second. We have an n and a k there. We read an n choose k. And the idea of the binomial coefficient is that it's counting how many ways we can take k elements from a set of size n. I'm still struggling with this stream deck, so apologies. So let's compute a few values of n choose k. So let's write this down. So n choose k, this is number of ways to choose k elements from a set of size n. Okay. So we have, say, n choose 0. I have this set of n things. I'm not going to pick any of them. How many ways are there to do that?
1.
There's 1. I just don't do anything. There's one way to do it. Let's see. How about n choose 1? I am just going to, from my pool of n objects, I'm going to grab exactly one of them. There is just n ways to do it. Now let's look at the other extremes. So, say I have, I want to choose n objects from my n set. I'm going to pick everything in this case. So again, I get this 1 here. And last, I think these are all good examples. If I choose everything but 1 element from my set, we can think about this, and this will be helpful soon. We can think about this as, which element do I not include in my set? If we think about it in that way, for any n-1 elements that we choose, we always exclude 1. There were n elements in our set, so there are n ways to exclude that element. I apologize if the audio has been goofy. I do not see the chat. Is it good, Van? Thanks. Okay, now let's, yeah, there we go. Let's look at some problems here. Just sort of leaving that up on the board, this n choose k. We might ask, so how many ways can we get 10 element subsets from the set 1 up to 100? Well, we have 100 items, 100 elements to work with, and we're just picking 10 from it. Just 100 choose 10. Unfortunately, this doesn't fall within one of those easy cases, so we're just going to leave it like that right now. We also might ask, so count the number of possible couples that can be formed from among 7 people. This right here is what
Corey was talking about at the very end with the birthday paradox is that we want to count how many possible couples can be formed. And you use this thing, this binomial coefficient, because all you get, you have 7 people, we're going to just pick 2 of them. 7 choose 2, and last, just counting the number of binary strings, length 55 with exactly 22 ones. Well, yeah, basically for every bit of your binary string, you have the choice between choosing a 0 or choosing a 1. You have 55 bits, and we're going to choose 22 of them to be 1s. And this idea of the binary string sort of fitting in with this sort of scheme that there are, say, 55 choose 22, so many that get us with exactly 22 ones, will be, it'll be helpful soon. Let's see, boop, boop, boop. Now, it's great and all to be able to write these choose symbols up here, but if we're actually going to use them to count, we might want to know like an actual numerical value. Well, luckily, we have this theorem that tells us that n choose k is actually equal to n factorial divided by k factorial and n minus k factorial. And if you see right here, I'll just draw it, this I didn't calculate these beforehand, so I'm not going to stop it. Okay, but if we look at this right-hand side, we have this n factorial divided by n minus k factorial. See this right here, this is our permutations of k elements from a set of n objects. So let's write that down. So this is our number permutations of k objects set of size n. Had to figure out the most verbose way of saying that, so I'd have to write. Okay, so we've seen this before, which is nice, and now what I want to sort of show, I like to draw this little exclamation mark over the equals, because this is what we want to prove. It's not true until we sort of reason it through, is this is k factorial times n choose k. If we can show that this is true, I can just divide both sides by k factorial, and I have the result that we actually desire. So, is it true? Does this count the number of permutations of k objects from a set of size n? Van is nodding. Yes, it does. Okay, good. Why? Well, let's see. So, n choose k, what is that? Well, that's going to count the number of ways to choose k elements from a set of size n. So this will just give us our alphabet. This is right now going to determine, we have n elements, I'm choosing this pool of k. Now, there are n choose k many ways to do so. Now that I have my k elements, permute them. So let's write that down. Choose k elements, and we permute them. And that actually is our proof. I wasn't here for the first hour of Corey's talk, so I think this might be the first instance. We call this a double count. Effectively, we say, hey, and here, let's move this guy away. There we go, because now it's true. That is an equality. We call this a double count. And the idea is if one side of this equality counts something and this other side of the equality counts the same thing, they have to be equal, even if they look different. Now, this is great. Now let's actually write this up here. We actually have a numerical value to our n choose k. Right on. All right, so now let's compute something. So we talked about cards, and we have already seen that to get all possible shuffles of a deck, we would need too long. That's a mathematical term. It means 10 to the 87 or something like that, I don't know. Anyway, so sure, there's that many ways to actually deal a deck, but what if we're just counting how many 5-card hands we can draw from this 52-card deck? See, what's nice about these choose functions is that they handle these cases of not caring about order. So even like we could draw, boop, 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 boo, son of a gun, big, there it is, yeah. We could have drawn, say, this hand, and I'll give them, I don't know, they're all hearts. We got lucky. Just to make the point easier. We could have drawn this in this order, or we could have drawn it, and they're all just gonna be hearts again. I don't feel like drawing that. We could have drawn it like this, but I mean, anyone's played some sort of card game, you just shuffle it to an arrangement that suits you. They are effectively the same hand. You will get a flush here, which we'll talk about how many flushes there are at some point. But the idea though is that we don't care, we don't need to permute these. All we gotta do is choose from, well, we've already said it, cool, it's in the problem. And I realize, oh, I am big. All right, cool. We have 52 cards in our deck, and we're just gonna choose 5 of them. Doesn't matter order, we're just choosing 5 of them. And now we actually can compute this thing right here. What does 52 choose 5 actually equal? Let's first write it out like so. It's 52 factorial divided by 5 factorial times 52 minus 5 factorial. And I have notes. I'm just going to grab them. Meant to bring them to me. There we go. So this is actually 25,989. There we go. Okay. This is 2,598,960. Okay. So there maybe is a possibility that enough people can see all the hands. That's good. So there's not that many compared to how many actual decks there are. So, boop. Okay, now what about this? So, okay. So an NBA roster, Corey is a big fan of basketball. I wish I was. It's not that I dislike it, there's so many names, and I feel like you gotta know this guy said something awful on Twitter, or this guy, he pulled his leg, and I'm just not really trying to figure all of that out. I respect that some people do, and they have really fun things to talk about, just like this, combinatorics. So, an NBA roster, it has 15 players, and both teams in basketball, I do know this, they only allow 5 players from each team on the court at any time, and because of that, there's a starting lineup for both teams. So we might ask, well, how many starting lineups are there for each team? Of course, there's kind of a lot fewer because you're not going to put your second string out there. Probably not in its entirety, maybe ever, I don't know. I'm not sure about the specifics of it, but I do know there are 15 choose 5 ways to do it. And what is that? It happens to be 3003. So that's a lot. That's a lot of starting lineups from a single team. Now, we might ask the following question as well, because an NBA regular season's got 82 games. So if I want to do every single starting lineup, and I only have 82 games a season, how many seasons do I actually have to go through? It is approximately 3003 divided by 82, which will be 37. So we'll have to play 4-ish decades of basketball to get every starting lineup. I'm not sure any basketball player has played 37 consecutive years, but if so, I'm sure that they were on enough of the starting lines. Okay, now this is a fun one. So this is, and also I do appreciate, I wish I had the background for all of these things, but this is also another thing from Corey. So Corey used to live in Hungary, and in Hungary, they have these bus tickets, or they used to at least, and you would get it punched in one of these 9 squares on the screen, and you could feasibly get away with just having every possible way to punch the ticket. Let's hope. We would feasibly have it all if we could count how many there are, maybe multiply that by the cost of a ticket. But if you did get the book for it, you just put a little card into the part of the bus that punches the ticket, look at your set of tickets, and pull that one out when the guard pops up. And just be like, oh, look, I totally have my ticket. It's great. Trust me. And I think Corey and Juja, his wife, definitely did this back in the day. They just have their tickets. I'm not saying, no, they didn't. They didn't do that. That's a crime, and bad things can happen to people who do bad crimes. So that didn't actually happen. I redact the last few seconds. But anyhow, let's sort of just look at this thing. So we have 9 squares, and it's validated by just punching these holes. Now, you just punch any amount of the holes. In this particular question, we want to know how many ways there are to punch 3 holes. Luckily, that's 9 choose 3. I didn't actually compute this one. This isn't that large, though. Now, what about 4 and 5 holes? I guess I should put an A right there. Well, that's fine. You can just do 9 choose 4 for the 4 holes. You could do 9 choose 5 for 5 holes. And just to sort of think about this visually, let's imagine we did punch a card in 4 spots. Boop, 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 boop. If we look at the spots that weren't filled, there were 5 of them. And in fact, basically, any 4 punched holes, I can get a similar card with the opposite holes punched in. That is to say, these two are actually going to be equal. 9 choose 4 and 9 choose 5. They count the same thing, sort of as I was saying earlier. If I'm choosing 4 things, I'm not choosing 5 things. So we determine the 5 things that we're not choosing to determine the 4 things we are. That's a mouthful. But it leads us to, the complement identity. Perfect. I'm just taking a sip of coffee there. Probably not the best. I probably need some water. So I'm gonna do that too, actually. 1 second. Okay. So we have this complement identity, which actually it fits with this little structure right here. Let's just write that, boop, boop, and choose K, and I'll put another exclamation mark there. And then N, choose N minus K. And I've effectively already sort of stated the proof of this. I've just used cases in each part. We can sort of say this for a general N and K, rather than say 9 and 4, 9 and 5. The proof is just that if I'm going to choose K objects from a set of N, then I don't choose N minus K objects. And that correspondence right there is actually effectively it, unless I'm mistaken. And then, boop. Okay, so with that in mind, let's look at these problems. Right, so back to binary strings. Let's see. I'm just gonna erase all of this. Think you believe me with this part. Okay, so now let's compute binary strings of length 100 that have exactly 45 zeros. And then, well, just sort of keeping with the rest of this section, that's just going to be 100 choose 45. Now, we can also ask how many have exactly 55 zeros? Well, that's just 100 choose 55. And now, I think just, of course, with tying back to the last few slides, these we at least think are equal. But let's sort of visualize another, let's sort of look at this visually. Let's pull a string with 45 zeros. I'm not going to draw it all, don't worry. But let's say we have this 0, this 0, this 0, bunch of zeros, a 1, another 0. And let's just say, I'm just going to say it, this thing's got 45 zeros right here. Oh gosh. Is there an E there?
I don't think so. It's spelled both ways on the slide.
Perfect. So I'm going to go with that one because confidence is key. Okay, so 45 zeros, trust me, they're in there. And that's zeros with 2 E's. Now, what's great is that if I were to say, look at this guy, where I just flip all of my binary strings. So when I had a 0, change it to a 1. And if I had a 1, change it to a 0. And then everything here was the same, whatever it happened to be. Wait, sorry. The same thing happens with what's going on in here, just sort of the flip. Any zeros turn to 1s, et cetera, et cetera. This thing right here, well, it has 45 1s now, so it has 55 zeros. So okay, I think looking at it this way, we see, yeah, there's like this correspondence between these two types of strings, so it is plausible and in fact true that we have the same amount. So how do these two values relate? Explain using the definition. Okay, I just did that. Awesome. So part B though, let's look at that. How many subsets of size 100 are there from set 1 up to 300? And again, this is same sort of idea, but it's no trouble in doing similar problems. So there's 300 elements we got, and we choose 100 from there. And then, or we choose 200 elements from there. And I'm gonna, I guess maybe I should just do a small example again, but just say I'm choosing from the set 1, 2, 3, 4, 5. If I choose all of the 3 sets, say I choose a 3 set, 1, 2, 4, there, if I chose these 3 elements, there's another corresponding element of size 2, 3, and 5 that I didn't pick. And this is sort of the essence of why, in this case, 5 choose 3 equals 5 choose 2. We just sort of correspond what we have to what we don't have. Now let's look at this fella. So now we have a problem of a different flavor. We want to find the coefficient of a cubed b squared c in the expansion of this polynomial. Now, it's a little bit different of a flavor, but luckily we're in this section, so we're probably going to use the binomial coefficient. Now, why? So we want to find this coefficient of a cubed, b squared, and c. Some number here, I'm going to call it k. We want to figure out what that k is. And we'll get it somehow from multiplying these out, but I don't want to multiply them out. I've done it before just to sort of see how nasty it looks on Wolfram alpha. It is gross. And but it's okay. We only need to find one little part of it. So how do we do that? Let's sort of expand. Let's just look at, let's look at the first 2 parts of this. So if I take a plus 2b plus 3c raised to the 6, that's the same as multiplying this thing to itself, a plus 2b plus 3c, multiplying that 6 times. Okay. Now, what we're trying to get is the coefficient a cubed, b squared, and c. So what we can do, or what that means at least, is if I'm multiplying these out, I'm only ever going to want to know when I get exactly 3 a's. So what I mean is, this one's got an a, this one's got an a, this one's got an a. When I multiply these out, they're going to make an a cubed with some other things, depending on what I choose from my other segments. Let's just say we're looking at just these 2 for now. I can choose this a right here, or I could have chosen this a. So what am I trying to say? I'm not going to go to the smaller case. It's sort of weird and contrived. Anyway, I'm just going to back up. So there's 3 a's that I want to get here. I have 6 different terms in my product. So what I'm going to do is from those 6 terms, I'm just going to choose 3 a's. And there are, in fact, 6 choose 3 ways to do so. I could have picked this first one, this second one, and this last one. I could have picked the second one, the fifth one, the last one, any combination of those three. So once I've done that, I am now going to pick my B's. I've already fixed 3 of these choices to be my choice of 3 A's. So I have 3 options left. I have 3 different spaces that I can actually choose from, and I'm gonna get 2 B's. So I'm going to choose 2 from 3. And there's another added factor here, is that there's this coefficient on B of 2. So whenever I pick a B, I have to multiply it by 2. I'm picking 2 B's, so we get this little 2 squared for the ride. Now, after I pick my A, I pick my 2 B's, I'm basically, it's determined where this C is going to end up. So and let's say it like this. There is one more space to choose from, and I'm going to choose one element from it. And that element is C. And C had this coefficient of 3 with it, so we got to multiply that in. This right here turns out is your coefficient. And we didn't have to do it that way. It actually truly didn't matter that I picked my A's first. We could have totally picked the C first. What would that look like? Well, I have these 6 choices in this product. So I choose one of them to be my C. That C brings along with it this coefficient of 3. Let's add these little dots to indicate I'm multiplying. And after that, I'm left with 5 options. I can either pick the A's, I can pick the B's. Let's pick the A's. Why not? 5 choose 3 many ways. The A's have a coefficient of 1. Last, we're left with 2 things, and those are going to be B's. And for both of those B's, I pick up a 2. And what we'll maybe see is that, yes, these 2 products, if you work through them, they're actually equal here. Okay. What do we do from there? Ah-ha-ha. Oh, was I small that entire time? Oh, gee. It's okay. Let's see. Okay. So, on to something completely different. So, we have Fisher random chess. It is this style of chess where, so your front rank, or not rank, oh gosh, somebody who really likes chess is gonna grill me on this, but so the front line of your defense, it's still pawns, but you have sort of a random arrangement of the other pieces that are allowed. And just to remind ourselves, we have 2 knights. Let's write the boop, boop, boop. There we go. We have 2 knights, 2 bishops, 2 rooks. You got your queen, and you have your king. Cool, perfect. And now with Fisher random chess, we have 2 stipulations. We can put our pieces wherever we want so long as these 2 things happen. Our bishops, the thing is with bishops, they can only ever go diagonal. So we want to make sure that they can go on the 2 different diagonals. You have your white and black diagonals. So let's see, So for these, we have them one on each color. And I think, and what else do we have? We have that the king must be placed between the rooks. Okay. And this is so that you can still castle your king. If that makes sense to you, you got it. Yeah, so if you just want to be able to do certain moves here, let's see, must be between your rooks. Okay. Any other things to add? Yeah, I believe that the idea of Fisher Random Chess came because Bobby Fischer was sort of bored with chess. Not bored, but maybe he sort of hated the strategy of chess, how it became. It was a lot about openings, and he was like, you know what? This is all because we have decided to put these 8 pieces in these particular spots. So why don't we just throw that away and try something different? You know, maybe there have to be these 2 stipulations to make sure it can still operate like chess in the mid game, but like phooey with this initial structure. So we want to count how many ways we can actually do our starting positions. So how many ways are there? So I particularly like to start this with the bishops. Again, from our last example, there are many ways to count the same things, so long as we, I guess, keep it consistent. I'm going to take this cap off. I keep fidgeting with it. I apologize if that's getting into the mic. Okay, let's start with the bishops. So our bishop 1, I'll actually even sort of map this out. So our bishop, we can put it on one of 4 spaces. Let's actually draw this back line. So we have, we got him. Okay, so we have the black spaces and we have the white spaces, and white is in the bottom right corner. We got him. Okay, so your bishop, so we have one bishop that's on the black spaces, one bishop that's on the white spaces. Let's see, for this one, let's just do the black space bishop. How many ways can we do it? Oh, that's not too bad. There's 1, 2, 3, there's 4 many ways. Similarly, with our white space bishop, well, we actually, it doesn't matter where our other bishop was. There are, oh, and here actually, I realize what section I am. There's 4 choose one many ways. Excuse me. Yes. Now, we put our bishops down on our field, so 2 spaces are taken. Say this one, say this space is taken, add a little bit of color back in there. There we go. And this space is taken. Cool. So let's add our knights. So how many ways can we move our knights? Well, I can put my first knight in any of these spaces, and I can put my second knight into another space. And it doesn't matter actually which one I chose first. They're the same piece, so it'll actually just be 6 choose 2 for our knights. Right, if I chose this one for my first knight, chose this for my second knight, I could have very well have done it the opposite way. Wouldn't matter, they're both knights. And last, let's see, we got our queen and there's one queen. So there's 4 spaces. I can choose any of those to get my queen there. And what's nice, actually, is with these last 3 spaces, we have these 2 rooks, and we have a king, and the king has to be between the rooks. So in fact, it's actually determined. Once we're left with just 3 empty spaces, say these ones, our king has to go in the middle space. So we actually kind of get this one for free. And maybe I keep saying the wrong pieces, so I apologize if this is confusing. The king and the rooks, they're determined after we have chosen everything in this line. Now, what's nice, and those who might be familiar with random Fisher random chess, is that if we multiply these out, we actually end up with 960. That is to say there's 960 valid starting positions. And this is actually another name for this game. It's just, or, excuse me. Again, somebody who really likes chess 960 is gonna hate that. There we go, the 960 comes in the end. There we go, wonderful. So, what else do we got here? Now, to real world applications. That is what I'm interested in. You talk about all this math, but how am I gonna make any money? We're gonna do the lottery. Not just any lottery, the Montana Cash with Max Cash lottery. This one, with this lottery, we pick 5 numbers from 1 through 45. It's like a bingo system, so the order does not matter. And we might ask, well, okay, if that's true, then how many tickets are there? How many possible ways can I get 5 numbers from 45 without worrying about the order? I have 45, I'm gonna choose 5. Okay, now let's think about this one. I've written some notes down. This is actually going to be 1,221,759. There's this many possible tickets. We might ask ourselves, okay, well that's cool. What is the population of Montana? If everyone just got a different card or a different lotto ticket, in just one, would someone win? Maybe not, but we'd be quite close. The Montana population, at least from the last census, I think, is approximately 1.1 million. So pretty close. Not exactly there, but only 100,000 shy. You know, if some people got 2 tickets, we'd probably get there. Well, we'd definitely get there, which is great. Somebody makes some money. Now, that's wonderful and all. That is for Montana in particular. Let's talk about, on the other hand, Powerball. Powerball is a lottery ticket throughout the United States. And with this one, it has a different rule. Now there's 69 numbers to choose from. And it actually, again, doesn't matter the order. It's like bingo. If a 5 comes in before a 4, nothing matters. It's 4 and 5. And after those 5 numbers are chosen from the first 69, there is this other number, this 1 to 26. Just one number that has nothing to do with the other choice. And so we might ask ourselves again, how many possible tickets are there? This isn't that hard of a calculation again. It's the same sort of idea. We're going to choose 5 numbers from 69 for those first 5 numbers. And then there are 26 numbers for the second. And we're just going to choose one of them. Awesome. Now, what is this equal to? Well, let's see. This is a lot bigger. So this is about, I'll write it nice with a million. This is about 1.2 million. Pretty close to the Montana population. With just a little luck, one of us would win. But in this case, this is 292 billion. Okay, there's a B now. That's wonderful. Well, how many people are there in the US? Does anybody know?
Didn't we say it was like 400 million?
That's about what I got. I think it was around 3. Yeah, the number I found was like 331 million with an M.
Oh, right.
Perfect. Okay, so somebody in Montana sure to win way sooner than here. This is, orders of magnitude are crazy. This is 1,000 more multiplicatively than that bad boy. So not likely you're gonna win, unfortunately. Now back to ASCII code. This is wonderful. Okay, so I might need some help here. Okay, maybe not. He's leaving. Okay, I'm trying to recall all of my ASCII, but let's see. So what are we asking here? How many 8-character passwords from the 95 ASCII characters use exactly 3 digits? Okay, so how are we going to do that, right? So the ASCII characters, there's 95 of them, but we want to use exactly 3 digits in there. So,
is that digit like 0 through 9? And then
yes.
Be whatever it wants to be?
Yeah, I'm trying to recall this. So with ASCII, there's 26 lowercase, there's 26 uppercase, there are 10 digits, and then 95 minus 26 minus 26 minus 10 other things. There we go. Perfect. So, and thank you. And so yes, it is 10 digits. So now we want to figure out how many ways there are exactly 3 digits. So how are we going to do that? Well, I have 8 characters here. And now I want to select 3 of these 10 spots. And I'm going to put some digits there. Say this one, this one, this one. I have a tool to figure out how many ways there are to do that. Luckily, there are 8, choose 3, many ways to select where we're going to actually put the digits. And so for each of those spots, we have 10 digits. So there's 10 ways to pick this spot, there's 10 ways to pick this, and there's 10 ways to pick this. Multiplication principle tells us then there's 10 cubed ways to do that. Now we want it to be exactly 3 digits, so I can effectively I can put whatever I want in these last spots so long as it's not one of my digits. And since ASCII has 95 characters, that means 85 characters are not digits. And there are 1, 2, 3, 4, 5 spots for me to decide where those go. And I didn't actually just sort of think with what's going on with this guy. Once I decided where my digits were with this 8 choose 3, we can think of this invisible 5 choose 5, which tells us that I'm left with 5 spaces, and I'm gonna use those 5 spaces to pick my other elements, if we want to think of it that way. And if we do, luckily this is just equal to 1, and everything works out. And so we end up with a lot of characters. I haven't calculated this one myself, but it is not as large as the number Corey found earlier. I'll tell you that, because we have a few restrictions. But let's see what else we can do. So now we run into some fun sort of, this problem is sort of different from what we have been dealing with thus far, because with using this choose function, we're working in a place of not allowing repetition, and not really, now we're dealing with repetition. And so we have this problem about anagrams. We ask, how many anagrams are there of eat? What about of I? So let's actually, let's write these ones out. I chose some small words to sort of figure this whole thing out. And also I chose eat because I think of its anagrams, there are a few that are actual words. This is nice. So we want to think about these as strings of characters. So let's see, with eat, this is actually just a refresher. If we want to figure out how many anagrams there are of this, well, we can just permute the letters here. I can choose 3. There's 3 choices for my first letter. There's 2 choices for my second letter. And then there's 1 choice for my last letter, i.e. 3 factorial choices, and otherwise known as 6. Cool, which those are, we got eat, got to include the thing itself, ETA, nice. Let's see, 8, maybe that's a Scrabble word. Now that's definitely a Scrabble word. Okay, and T, perfect. All right, so what's nice at least with a word like eat, or a string like eat, all of the letters here are distinct, so we can just permute them around and not really worry about what happens. We're gonna get different things in this sort of scheme. Now with I, it's a bit different. So I can choose E as my first letter, okay, and then if that happens, well, let's do Y as my second, E as my last, okay. If I do E as my first, I can do E as my second, we get A. Cool. Now, notice here, these two are not distinguishable. This, I could have thought of this as like the first E from here, and this is the second E, but I haven't labeled it as such, so this is the same as doing this, even if this to me was the second E of I, and this was the first E. So we want to make sure, indicate those are the same thing. Now, we have E, and what else do we got? We got Ye. Cool. And then I think that's it. Okay, so now with this repetition here, we actually, well, I guess it's sort of clear here, we halved our possible anagrams here. Now how do we actually figure this out using binomial coefficients? Well, it's sort of like our, I think, was that? Yes, it's sort of like with this ASCII problem. We're going to first just sort of separate these in two groups. I can think about this, I have two E's and I have one Y. Now, and I have three total spaces for what I'm gonna do with these E's and this Y. For the E's, I'm just going to choose two of my spaces from the three possible choices. And I'm just gonna throw the E's there. It's nice, we had like a binary choice here. I could have an E in a spot, I could not have an E in a spot, without ever considering what's happening with the rest of my alphabet here. And yes, there are just these three ways to choose two spots for my E's. Once I've done that, well, I have one space left and I only have one character left. So we actually do get this nice, just three anagrams here. Which, okay, that's our little baby example. Let's do something cool. How about, and I have space for it, let's look at matrices. Okay, matrices. Did I spell that right? Yes, okay. So what's happening with matrices here? We have, excuse me, we have a bunch of letters that are duplicated here. Let's actually sort of with this, let's just take stock of what we have. We got one M, we got one A, we got two T's, we have one R, three S's, and two E's. I don't know why I skipped the E, whatever. Okay, so we have all of these, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots. And we're gonna do this sort of idea where we say, hey, with these particular letters, say, let's start with T, I have 10 choices of where to put my T's, and I'm gonna just lock them in. I have 10 choose two choices because I had 10 options and I have two characters. Now, so this is where my T's are going. And once I've fixed where my T's are, I only have 8 options. So I'm gonna, I don't know, let's do M, why not? I'm gonna move that M to one of those 8 spaces. There are 8 choose one ways to do it. Sweet. And so forth and so forth. I really should have done this in order, so let's do the A next. There's 7 spots, and I can do it one way. Now we're up to the R. There's 6, and I can choose one of them. We have now 5 remaining, and I can choose 3 ways for my S's to go about. And last, there's 2 choose 2 ways to finish this word with my 2 E's. And yeah, let's just do it. And one of the key things here is that it didn't matter the order that I chose things. I could have done the sensible thing and actually started with the M here. And we will end up with the same answer regardless. Kind of the cute thing of this. Bam, cool. I actually did not matter how we did it. Okay, and now last we have how many trinary strings of length 55 have exactly 22 ones and 11 twos. Okay, we haven't talked about trinary strings, but if you trust me, we will have a good idea of it just about now. So binary, you add zeros and ones, but it's also just an alphabet of 2 characters. Trinary is you have the digits 0, 1, or not digits, I'm sorry. Would they be trits? I don't know what you would call these. But trinary characters 0, 1, and 2. And we are going to build some strings of length 55 that have exactly 22 ones and 11 twos. So much like the rest of these problems, we start off with how many spots we have available. We're going to choose where to put our ones. Then after we've decided where our ones go, we are only left with 33 spots. Of those, I want exactly 11 of those to be twos. And my alphabet is zeros, ones, and twos. So let's write this. This is counting how many ways I can move my ones. Bless you. Positions for ones. Here we have our positions for twos. So we only have zeros. We can only build the rest of our string rather, from zeros. So we have 22, choose 22 ways. Perfect. And as I was sort of saying down here, this is a shorter example, so maybe a little cleaner. We didn't have to do it in that order. Of course. I get it now. I could have chosen the twos first. So I had 55 choices, and I wanted 11 twos. Now I want to know what's happening with my zeros. I know that out of the rest of the word, which we have 44 parts left, I know that 22 of them have to be ones, so 22 have to be zeros. Right on. And after that, we just have how many ways to get our ones. So this is ones, this is zeros, and this is twos. Turns out, doesn't actually matter the order that we chose it.
How many orders can you do it in?
How many orders can we do it in? Great question. Does anybody have an answer?
3 factorial? Yes.
Bingo, bango. Yes, we have 3 factorial ways to, I guess, build, or orders. To build anagram. Wonderful. So now let's look at this. Oh, yes. Now we're on to a new section. We have been able to get through everything with just multiplication thus far. So we want to add a few little bits to this. We got the addition and subtraction principle, and don't believe the hype. There actually isn't a division principle, at least not to my knowledge. But the llamas and sloths, they'll get to it later. So that's perfect. I don't have to deal with that. So, let's look. So what do we got? Perfect. It's in the title. That's great. So we have the addition principle. So what is the addition principle telling us? It's saying if I have so many ways to do one thing, so many ways to do another, and I can't do both of them at the same time, then if I want to count the number of ways to do either thing, I just add them up. So let's look at a few examples. So for instance, looking at our slide, where are we at? There we are. Looking at the opening slide, if you want to adopt a pet, which please adopt, but also spay and neuter your animals. So very important. So if you go to a pet store, you got 9 dogs, 7 cats, you can only take 1 home. How many options do you have? Just add up the 2 numbers. And yes, we're supposing that you're just choosing between a dog and a cat. Maybe you wanted a fish. But in this case, you wanted a dog and a cat, so you only have 16 choices. What else can we do here? Well, we can count binary strings. I know, so if we were to look at, say, binary strings of length, let's go length 8, sure. So let's look at binary strings of length 8. Now, we know the answer for the number of this is just 2 to the 8. Cool. Now, what if we wanted to try and calculate this some other way? Maybe with 2 sets that do not intersect at all. Maybe that's a bad word to use here. 2 sets that that don't share anything among them. So let's look at, say, let's look at these strings. Starting with 1. Say we just fixed our first digit here. Still leave it with 8 bits in our string, but we start off with a 1 here. Well, just using the product principle, we have 1 times 2 times 2 times 2 times 2 times 2, just end up being 2 to the 7. Because we fixed that first one, and then there's 2 choices for everything else. We can also calculate the number of strings that start with a 0, right? If it doesn't start with a 1, it starts with a 0. In fact, we'll actually get the same count here. We get 2 to the 7. And I guess I just said it a second ago, but these are the only 2 ways to build your binary string of length 8. You either start with a 1 or you start with a 0. So we actually have 2 to the 8 equaling 2 to the 7 plus 2 to the 7. Nice. Which just to convince us, I suppose. If we were just adding these, that's the same as 2 times 2 to the 7, which there's a 1 there. And we're multiplying the bases, so we add the exponents. Perfect, okay. This is my favorite type of proof. We have the same thing on both sides of the equal, so you know it's true. And last, yes, I think this is a good last example. We can add cardinalities. So, yeah, I think, I can do away with this and maybe write smaller. Okay, so let's look at this cardinality here. So if I have a set 1 and 2, now I'm going to add to it the cardinality of the set 3 and 4. Why does this matter? Why is this connected at all to what I've been saying thus far? Well, there's a 1 over here. There's no 1 over here. Similarly, 2 over here, no 2 over here, and vice versa. These sets, they don't share any members between them. They are said to be disjoint. That'll be important in Van's section later on. But for all intents and purposes, we can just say this is the same, the cardinality of these two sets added together is the cardinality of the set just containing all the items, since there was, since they didn't share anything, and that is just 4. Okay, so with those examples out of the way, let's look at ASCII codes again. Okay, so now we want to ask, well, how many passwords can we build that are between lengths 8 and 12? And let me just pause for some water. Now, up until now, we have just been asking about, say, strings of a fixed length. We ask, well, how many are there of length 8? How many are there of length 9? To figure out this one, we sort of just note that if I have a code of a certain length, then it can't be a different length. So if I know how to count the number of a certain length, there won't be any mishmashing. We can add them up without any problem. So let's actually do that here. So if we want to count how many ASCII codes are of length 8, let's do that. So length 8, done this before. There's 95 options for each of our spots of the code. And as I was saying, all length 9 passwords, yeah, you could find all of your length 8 passwords sort of living inside, but that's not the same thing as what we're discussing here. This is all the ones that are exactly 8. These are all the ones that are exactly 9. Again, there's 95 spots for each of them, but we have 9 choices. And we can just add those. We can just add them because there's no double dipping here. We can just sort of do the same for each possible length. Perfect. And we wanted to be inclusive, so we go from 8 to 12. And I wish I calculated this, but it's a little big. It's big number. It's bigger than just this one by itself, that's for sure. So what else can we do here? Yes, bringing it back to Montana. That's what I like to do. Okay, so there's this nice formatting thing that happens in Montana license plate. I looked this up before, and I feel like there's like maybe 1 or 2 other states that does something similar to this. Not in California, where I'm from. We don't do anything like that. I don't know what the logic is there. Here, it's actually kind of nice. You know, there are 56 counties in Montana, and each of them has a code, and that code is the first 1 or 2 digits on a Montana license plate. I understand that this isn't the only way that they've done this, but at least for my case, this is true. I have a Montana license plate, and it starts with a 4 because Missoula County is 4. But now, why am I talking about this? Well, we're going to count how many actual license plates there are. So with this format, we are in 2 different positions, because if we have a 2-digit license, 2-digit county code, then we fix those 2 numbers, and then we have 5 different spaces for our last last characters, where I'm trying to make sure there's nothing else crazy. Yeah, okay. I was gonna say I couldn't remember if there was a stipulation that the last character had to be a letter, Maybe it does. It doesn't say so in the question, so I'm just gonna assume it doesn't matter. But anyway, if you are in the case where you have this 2-digit county code, you're not in the case where you have a 1-digit county code, so we can count them separately and then just add them up. So how do we do that? So we have 56 counties. Just write that down. We have 56 counties, and the county codes go from 1 up to 56. So there are exactly, 9 1-digit counties. That leaves us with 47 2-digit counties. Perfect. Okay. Now, if we're in the 1-digit case, there are 9 choices for our first character, and then we have 6 different, 6 more characters, and for each of those, we can do a letter or a number. So we have 36 choices for each of those, and there are 6 different characters there. So we fill it up like so, or if we have a 2-digit county code, we go 47, there are 47 of those, and we're now left with just 5 characters, so multiply that by 36 to the 5. And we are happy. And I really wish I calculated this, but I think this is a bit over, bit over 1 million, so we still have plenty of license plates. That's good. What else we got here? Ha ha ha. Now what about counting subsets of sets? Okay, so maybe we have an 100 element set and we want to figure out how many subsets have certain sizes. Well, for this first part, that's nice. Well, we can pick 5 elements, or we can pick 6 elements. Nice. What about if we go between 25 and 50? We can pick 25, we can pick 26, we can pick 49, we can even pick 50. But luckily, in each of these cases, or none of these cases overlap. If I pick 26, I didn't pick 25, et cetera, et cetera. So all of these, we can just add them up. Nice. So what about, how many binary strings of length 20 have at most 5 zeros? Okay, so if we want to count at most 5, then that is another way of saying we have no zeros. We have 1 0, we have 2 zeros, 3 zeros, 4 zeros, 5 zeros. Okay, so, and how do we do that? Well, we have 20 spots. We can choose no zeros. We can choose 1. We can choose 2. Yeah, I'm just gonna, not even gonna write the other ones. Or 5. Right on. Now, what else? Yes, and now we have this one way to look at it. So with the binary string example, if we wanted to count, here we go. Yeah, if we want to count, say, all of the binary strings by how many zeros they have, we could have continued this process of 20 choose 0 plus 20 choose 1 plus 20 choose 2. Keep adding. Let's just do that right now. Up until I went all the way to 20 choose 20. All of these just counting how many zeros I've decided to put in my string. If I add all of these up, then I have all possible binary strings, effectively, or the count of all binary strings. And that's what this next, this next slide states, which is that if we add up the binomial coefficients, fix our top value, fix this n, and we add up all binomial coefficients with that up top, that is going to be equal to 2 to the n. So let's write that here. Bow. Okay. So the claim here is that this, for instance, is equal to 2 to the 20, which, as I was sort of describing it, I hope, because this is saying, all right, binary strings with 0 zeros, 1 0, 2 zeros, 6 zeros, 20 zeros. I found one of the binary strings along the way. I counted it. And binary strings, another way to count it is at every point, do I have a 1 or do I have a 0? There are 2 to the 20. So let's actually prove this in general. I think it's a little more helpful than looking at a specific case. That is, and we're not gonna, oh yes, I think I just said that. But yeah, let's look at it. So the number of binary strings of length n, yeah. If I go length n, I can decide how many zeros I put in my string. Boop, 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 boop. So, you got 0 zeros. Maybe not do that. Got 0 zeros, 1 0. It's still terrible. This is bad. Okay, 1 0. Once we get to the letters, it actually makes this a lot easier. n minus 1 0. Sure, that makes sense. Or n zeros. And if we decide how many zeros we have, we count all possible ways to do it, that will give us all of our binary strings. So let's use that idea up next. Ahaha, perfect. Now, we said it at the beginning, we have the subtraction principle. It's up at the top too, that's good, okay. We are alluding to it. So now we have this concept, it's called a universe. We don't have to really go too far into it, but the universe is all possible objects in a given situation, and if we have this set A that lives in our universe, say binary strings is our universe of length n, and we have this set binary strings starting with 0, then we have this concept called the complement, which is all of the sets within your universe that are not part of the set you've chosen. So in this case, if my set was binary string starting with 1, yes, then my complement would be binary string starting with 0. And what the subtraction principle states is nice, is that if I want to figure out the size of my set, if I know how many possible objects I could have picked, and I know the complement of my set, I can just subtract those two cardinalities and end up where I want to be. So let's, oh wait, what am I doing? Yeah. Okay, so let's count the number of binary strings of length n that have at least one at least 1 and 0. I'll just say trying to do this with the addition principle will be annoying, but that's okay, we just learned the subtraction principle, so let's think about it that way. So if we want there to be at least one and at least one 1 and at least one 0, let's just sort of consider strings that violate this. We want to talk about bad strings, because if we know what our bad strings are, we just throw them away and we're left with only good strings. So let's see. If we want at least 1 1, I know a string where I'm never going to get a 1. Just take the string all zeros or all circles. Take this one. This is the only time we're never going to get a 1. if you try and change any of these to a 1, you got a 1, I'm telling you. So there we violate our first condition. There's no 1 here. And of course, if I can also have it so there's no zeros. This is the only way to do so. And by the subtraction principle, I know there are 2 to the n many binary strings of length n. There's only 2 here that violate my condition here. So there are this many good strings. Let's look at another sort of basic example. Let's see. So a teacher's having a rough day. They are just trying to sit their 5 students down to watch, I don't know, TV. They had a rough night too. And so they know there's 2 students in particular, Larry and Jeff, who once they start sitting together, they are going to cause a ruckus. So they want to avoid Larry and Jeff sitting together. So let's figure out for the teacher how many ways they can do this and show them that it's actually going to be quite easy to avoid this situation. Okay. So let's look at this. We have 5 seats. And just like with cat and row, if you're familiar, if you've been tuning in for quite some time, what we can do is we can sort of lump Larry and Jeff as one unit and just sort of say, hey, if they're sitting together, we can just sort of have these chairs be like that unit. So what I'm trying to describe is if the ways that we can sort of pair them next to each other without worrying who's sitting on what side or whatever, there's going to be 4 ways. I can have Larry and Jeff sitting right here. I can have Larry and Jeff sitting here, right here, or right here. Those are 4 ways that 2 chairs are going to be right next to each other. And I said we didn't care about order, but I do care about order because Larry sitting right here and Jeff sitting right here is not the same as Jeff sitting here and Larry sitting here. Okay, so we have 4 times 2, 8 bad seatings. Oh, geez, that's a lot. Okay, well, how many seatings do we have at all? Well, if we don't care about Larry and Jeff wherever they're sitting, then I had 5 choices for my first. I had 5 factorial many choices for seatings, which if you do a little calculation, and I often forget, is 120, right?
Yeah.
Yes, thank you. I just wanted confirmation.
Yeah.
So this is how many possible seatings. Let's just write that. So thankfully, we have 120 minus 8, or 112 good seatings. Oh, good.
There's a question in the audience. I think you missed something.
Oh, I sure did. What did I do?
Well, let Anna try it.
Yes.
For each bad seating where Larry and Jeff are sitting next to each other, do we have to consider the number of ways that we could seat the other 3 students?
We sure do.
That's an easy fix, though, right?
That is an easy fix. Okay, let me just erase this. Okay, let's again, thank you, audience member, for 2. And now, these fellas, whoever else is remaining, we can sit them in any permutation. And there was just, let's just say, Larry and Jeff are sitting right here. Then I had 3 spaces left, and I'm just going to permute those. Thank you so much, audience member. It felt like something was wrong here. Okay, good, because there was. So in fact, there's actually, 8 times 48. Okay. There are this many bad seedings. So in fact, there we go. That makes more sense. Thanks. Perfect.
I would have used the calculator.
This is hard when you've just been standing here for a second. I'm sorry. But perfect. The real thing, well, let's just make sure. The real important thing here is that it was actually easier, even if I flubbed it, it was easier to count the bad arrangements here to figure out the good arrangements. Now let's look at this next problem here. So we have a stair-step number. Okay, so a stair-step number, it's kind of cute. It is a number whose digits are strictly increasing left to right. You know, they're going up, like a staircase. So how many, we might ask ourselves, how many staircase numbers are there? And nope, wrong one. Figuring this out every single step of the way. Okay, so, but what I'm concerned with is how many positive integers containing 2 or more digits are staircase numbers. Okay, so how are we going to do this? I'm gonna just sort of set up the basic structure before we get into the problem. So, oh gosh. Okay. So, number of staircase numbers. Yeah, if I subtract from this, yes, the number, I'm gonna actually, let's figure that out in a second. Because what I'm really looking for is the number of staircase numbers with at least 2 digits. Okay, if I'm looking for the number with at least 2 digits, then if I can just find all of my staircase numbers, if I just subtract off from those the ones with 1, yeah, I'm gonna add a little bit, or 0 digits, then we have what we actually need. This at least, at most, if you see something like that, there's a good chance a subtraction will help you out. I'm gonna take one sip of water. Okay, so let's actually do this. And the way we're going to go about it, let's just look at the longest staircase number there is. Yes. In fact, we can only use the digits 1 through 9 because we're actually looking at numbers, not strings. So we won't actually ever have 0 leading. Now, what's nice about staircase numbers, if they're always just going to be these increasing sequences, all we have to do is just choose a subset of our numbers right here. Because once we've decided which numbers from 1, 2, 3, 4, 5, 6, 7, 8, 9 we're going to pick in our number, there's only one possible way to arrange it. Once if I picked 2, 1, and 7, the staircase number I get is 1, 2, 7. So I can think about this as just choosing however many elements from a 9-element set. And so we can actually say right here that the number of staircase numbers is 2 to the 9. Careful. If we're counting all of these choices, 2 to the 9 is also going to include when I haven't chosen anything. So let's make sure to clear that away. So that's how many staircase numbers there are. How many of those are going to have 1 or 0 digits? I actually realized that was sort of here in plain sight, so I'm not even actually going to worry about that anymore. With 1 digit, yes?
Is 0 not a stair-step number?
Oh gosh. So 0 is a stair-step number. But that's okay. That'll still be part of this. Oh, I see
But
though.
then you just don't have to subtract the 1, I guess.
You're right. Yes, actually. So what Anna is pointing out here, yes.
They have
But-
to be positive integers, right?
Oh, there it is.
No, wait, I'm not sure.
Yes.
No, but the definition actually, right.
The definition doesn't have to be a positive integer.
Mm-hmm.
So they'd be excluded for,
Yes.
I think typically 0 is not part of this problem, but I mean,
If we include 0,
they
we'll,
should solve it.
fair enough. I'm going to include 0. Let's
Okay,
just
great.
do it. Okay, then I don't actually subtract from right here. The absence of one of these numbers is just going to be 0. Okay. And so a 1-digit staircase number would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 options there. Therefore, that's how many staircase numbers have at least 2 digits. If we include 0.
Ryan, could I ask a follow-up?
Please.
If you don't mind?
Yeah.
What if we didn't want to count those of length 2 either? Would it be hard or easy to modify this?
I think it wouldn't be too hard. Let's see. If we want to exclude staircase numbers with 2 digits, then we can't have, we'll be back in this sort of scheme where we don't have to worry about 0 ever again. And then we're just, we're just in the case where we're just picking a 2 set from 9 characters. Yeah, thank you. Okay, so now we've been talking about this complement of, thanks, John. Now we're talking about this complement of a set. We've said that the number of ways to choose such and such elements is the same as choosing the other elements. Now, why is that? What does that mean? How is this all connected? Well, if I have a subset of size k from an n element set, let's actually write all of this down sort of in a math way. So if we suppose that this cardinality of A is equal to k, then we might ask ourselves, well, then what is the cardinality of our complement? Well, our universe is this n element set. So if my set has k elements in it, then all the elements that are not in my set, they roam in the rest of those elements. They live among the n minus k, or they are the n minus k elements, rather. Yes, we had n total, so if I had k in this set, there's n minus k in my complement set. Ah. So now we might ask this question. Why? How is this gonna be solved? We ask how many numbers from 1 to 1,000 are not divisible by 5? Why didn't we ask how many are divisible by 5? Trick question, they're the same question. So, how many numbers from 1 to 1,000 are not divisible by 5. Let's figure out the ones that are divisible by 5. Let's do it. Okay, so this is actually nice. We can just sort of start from the beginning. 5. 5 is divisible by 5. And now we got 10. And we can keep going through this. What are we going to get? We're just going to get multiples of 5. We can think of them as 5 times a number. We end up all the way at 1,000. And right before that, 995. This isn't the nicest way to write this. This isn't going to make it as clear. Let's rewrite this. So we have 5. 10 is the same as 2 times 5. And 100, that's just 200 times 5. And 995 is 199 times 5. So what that means is, or here, actually, one more. There we go. 1 times 5. What this can actually sort of tell us is this is divisible by 5, this is divisible by 5, all the way up to here. And this actually gives us our count. There is going to be 200 numbers between 1 and 5, or 1 and 1,000 that are divisible by 5. They're right here. 1 times 5, 2 times 5, 3 times 5, 199 times 5, and 200 times 5. A fun trick, if it's equivalent, but another way to get here is if you just take the largest number in your set, divide by the number you're looking for, 5, you'll end up with, well, if we chose the numbers right, you'll end up with the count. If we went up to 100,000, well, that would be slightly bigger than 200, but that's okay. What we want is just the largest number that's almost there. Say if we did increase our boundary here. So now this is great. We have 200 numbers that are divisible by 5. So number of numbers not divisible by 5 from 1 to 1,000. Well, we had 1,000 numbers, and by this we have 200 that are divisible. So all the other ones, those 800 left, are not divisible. Divisible. Perfect. Okay. Now let's look at this. And again, I like to just emphasize like the flavor of these problems. We are asking for at least in this one. I should make it bigger so we can actually read it. There we go. So this next problem, we're talking about ASCII codes, ASCII passwords again. Now we're asking how many 8-character passwords use at least one symbol. See, if we say at least one, I want to do a subtraction here. Why is that? Because if I know how many there are without one, perfect. Then I didn't have to do at least one. Because if I want to count at least one directly, I check how many have 1, how many have 2, how many have 3, how many have 4, all the way up to 8. I don't have time for that. I do, but maybe...
Feel free.
But I don't want to. So let's do it the easier way. Okay, so just to remind myself, I already wrote this up earlier to remind myself. A symbol in this context, that was the word I was looking for earlier. It's what is not a letter or a digit. In ASCII, we have 26 lowercase letters, 26 uppercase letters. We have 10 digits, 0 through 9. And then what remains are symbols, which is...
Subtraction principle problem.
Perfect. 95 minus 26 minus 26 minus 10. Perfect. And we got a laugh. That's great. Which is the number. That's good. Okay.
How much?
How much is it? 33. Thank you, Dan. Okay. So we have 33 symbols. And now we want to make an 8-character password. And I want it so that we never use a symbol. Never at any point am I going to use a symbol, because if I know that count, subtraction principle, let's go. Okay, so let's see. You know what's great? I actually wanted the other number. I wanted 95 minus 33. Let's do that. Perfect. 62. Okay, there are 62 non-symbols. So, building up an 8-character password with just non-symbols, there are 62 to the 8 ways to do so. Boom. Just 62 at every choice. And of all 8-character passwords, there are 95 to the 8. So, perfect. That's our guy. This is...
What's that equal to?
Yeah, what is that equal to? It's the number... yeah, could somebody look it up?
Sure.
Number of ASCII passwords with at least one symbol.
6.4 times 10 to the 15 or so.
6.4 times 10 to the 15.
I think it's worth comparing that to the 95 to the 8.
That's what thank you. I was actually going to ask.
6 times 10 to the 15. So it doesn't do anything, right?
Yes. If you notice, if we just exclude ourselves to non-symbols, or I'm sorry, if we make sure to include one symbol, we get most of our passwords. I guess that's another way to look at it. If you didn't have a symbol in your password, you'd be compromised quite fast, I suppose. I don't know how you want to really evaluate. It'd be 2 times 10 to the 14, which is still large, but in these terms, I guess, smaller. Ahaha. Now to the real meat and potatoes. Okay. So I was talking about cards earlier. We talked about it before that as well. So we first were counting how many ways there are to have a 5-card hand, which is around 2.5 million. But let's re-examine that. I didn't really talk about cards that much when we did this. We just knew there were 52 cards, and and they were all distinct, and we wanted 5 of them. That could have been any sort of playing cards, but let's just talk about the usual bicycle sort of cards. So in this sort of scheme, we have, ranks and suits. So the rank is the little character at the corners of your card. We have ace up to, which is like a 1 or a not 1. 2 through 10, jack, queen, and king. And we also have suits going from top to bottom. We got a club, we got a spade, we have a heart, and we have a diamond. Just for our American viewers, because I didn't know this until I played RuneScape, a spade is a shovel. That little symbol right there is a shovel's head. Makes sense to me now. And a club, yeah, I don't know, it's a clover. Somebody probably knows more about that than I do. Well, they definitely know more about that than I do, because I just see a clover, but it's a club. So what are we actually going to do here? I didn't go to the next problem. We're actually going to count our hands. See, when you're playing poker, you want to win. And how do you win? You get a good hand. And the thing is, the way that poker is sort of structured is that rarer hands trump less rare hands. So let's figure out the actual counts of these possible hands. And I'm not sure the order that I have written here is the way I'm going to go about this. I sort of flip-flopped about how I want to do this. So I'm just going to write down the actual sort of hand that I'm working with at any point rather than the letters. We're gonna start from the top. So if you're playing poker, you really, 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 really want to get a royal flush. You win if you get a royal flush. A royal flush being you have everything they're all the same suit, so heart for instance, and you have an ace and then 10 through king. You're gonna think of that as 10 through ace because ace is sort of this low-high card. Now, what's great about that is, well, there's only one way to do it for every suit. If I have a royal flush, so let's count this. So there's 4 suits, and there is 1 arrangement, let's say. Because we've sort of determined that if I'm gonna get a royal flush, we know what cards they are. It just matters that they're all the same suit. We've already fixed that. There's only 4 ways. So yeah, it makes sense that this is your tip-top hand. And right below that is the straight flush. See, the royal flush is actually just an instance of the straight flush. It is a specific version of it where they're the highest cards in the game. A straight flush is just, I guess I haven't explained what a straight is or what a flush is. So let's do that. So a straight is 5 cards in a row. That's like ace, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. That is also a straight. And a flush is having all of your cards of the same suit. So when I built that straight, it actually didn't matter if I'm just worried about it being a straight. It didn't matter if I had an ace of spades, 2 of hearts, and then 3 spades, 4 spades, 5 spades. Didn't have to match. But for a straight flush, I needed all of those to also be spades. So what do we do here? Well, with a straight flush, I need to know how many, they all have to be the same suit. So there's 4 of those, awesome. Now how many actual straights do I have? Well, turns out it's 10. The way we can sort of think about that, is it 10? Wait, let me make sure I got that right. Let's see. The way I like to think about it is what's your highest card, how many highest cards there are in a straight. We can do 5, 6, 7, 8, 9, 10, jack, king, queen, king, ace, 10. There we go. So there are 40 straight flushes. However, in that scheme, I sort of did a little bit of over counting. I did the royal flush here too, right? I said I let 10, jack, queen, king, ace be one of my straight flushes. So if I want to just get all my straight flushes, I'm just gonna subtract that count. And we're still in the numbers that are easy to calculate. So this is just 40 minus 4, 36. There's 36 straight flushes. Yes, Noah?
Are we counting ace as a high and low card?
We sure are.
Okay, so that's how there's 10. I was thinking of maybe B9. Yeah.
Yes. Yeah. Ace is high and low in this case. Very important.
And I think in this case, I think by the rules, probably there's 40 straight flushes. And here you've counted 36 like non-royal flush straight flushes or something.
Precisely.
Precise, right?
Precisely. Well, yeah, because I mean, if you had a royal flush and I had a straight flush, you would win.
Right, but we could, yeah.
It would. I mean, it is a straight
I
flush.
think
It's
it's the only instance where a subset situation comes up, right?
there's actually one other place.
Okay, great.
Yes, there's going to be a few that we can count multiple
Well, a
times.
flush would count.
Yes,
Okay, I see. All right.
precisely. So let's get to the next one. And just looking at here, the next rarest is a 4 of a kind. So let's do that. So with a 4 of a kind, I want 4 of the same rank. And in that case, the suit doesn't actually matter because we get all 4 suits. So in this case, I'm picking one of my 13 ranks. So let's do that. So choose 13 and, choose one rank out of your 13, and then we just get a 5th card. Luckily, we already got all of our cards of a certain rank, so we're just going to calculate, what is this?
It's 48 left.
48, thank you. Yeah, there's 48 left, and we're just gonna choose one card from that. This is 624. Yes, which as we continue, we will get increasingly larger, which is nice. Now next we have a full house. So what are we doing here? So a full house is a weird sort of hand. It's to me, it's like the weirdest of the main ones. The full house is you have 2 cards of the same rank, 3 cards of a different rank, but all the same. So in this case, if you had 2 2s and 3 3s, that would be a full house, for instance. And so how do we actually do this? Well, we're going to choose 2 ranks. So we have 13 to begin with. We're going to choose 2 of them. And after we do that, we, brain fart. We're going to pick 3 from one of those. So we have 4 suits for any rank. We're going to choose 3 cards from one of them. And then we are going to choose 2 from the other. And I feel like I'm missing a step, but that's...
We need to multiply by 2 to pick which of the 2 we chose.
Thank you. Perfect. Appreciate it. Yes. And it mattered in this case which of these 2 we're actually going to get 3 of. Yes. And in this particular case, we get 3,744. Okay, we're building up. Yeah, it'll be super likely to get a full house. I actually, now that I think about it, I should put it explicitly on the board just to get this in the mindset. So, number of possible hands. Probably should have had this out here from the get. What is this? Well, we already found this to be 52, choose 5. And that is 2,598,960. So, okay, maybe not quite, but that's all right. We're getting bigger. We're growing up. So what's next? We have a flush. And as I said before, flush, they are all of the same, suit, but not but not in order. If we get like ace 2, 3, 4, 5, that would be a straight flush. So we want to avoid that. So how are we going to do that? Well, let's choose our suit. Okay, there's 4 choose one many ways to choose our suit. And from that, well, I'm going to choose 5 cards. There we go. But I counted my straight flushes, and I don't think I count them multiple times. Make sure, yeah. This.
But your royal flushes should be good too, right? Yeah.
Thank you. But also, we have our royal flushes. So now, number of flushes minus our straight flushes minus our royal flushes, or I'm sorry, yes, this is all possible flushes that include these folks. And now we just sort of eliminate those by subtracting out. Perfect. And what's this? Because I want to keep up the theme. This is, where did it go? 5,108. So it's only slightly larger. There's sort of, we thought there might have been, I thought maybe there might have been a theme of increasing like substantially, but of course, at the end of the day, we have 2 million. So at some point, we got to have things be sort of close. Now, what's next? What is a flush beat? Flush beats a straight. And this one always gets me. I always forget which one's larger. Hopefully, this will.
Have a definitive answer?
Yeah, this will keep it quite concrete. Okay, so a straight. Already discussed. It is just 4 cards in order. So 5 cards in order. If you get 4 cards in order, you really hope. You're praying that 5th one drops. Is it going to be an inside? Okay, so what do we do here? So we can believe we're good to just say, yeah. What do I want here? I'm going to choose, just sort of think about it this way. I'm going to choose.
Maybe a high card first? I don't know, it's just a suggestion. I don't know.
That's what I would think. Yeah,
Right? The high card or low card defines
Right.
the straight.
totally. And there was, what did we say, 10? 10 of those.
Oh, we did that already with the straight flushes.
Yes. So there's 10 possible low cards. And oh gosh. I'm just trying not to, I'm worrying about overcounting a lot. And okay, so there's 10 low cards and we can decide just the suits of everything. So this is going to be 10 times 4 to the 5th. There we go. That gets us all of our straights plus all of the bad ones. Or wait, just these. Just these. Cool. Perfect. Which is going to be 10,200. Wonderful. Which is kind of fun. That's telling you that this one, these two right here, these quantities are basically, that one's practically double. Very cool. What do we have next? We got ourselves 3 of a kind. Okay. So how do we do this one? We gotta pick. Our card. So let's choose it. So we have 13 ranks. We're going to choose one of them to be a 3 of a kind. And then, well, there's 3. There's 4 cards of every rank, and we're going to choose 3 of them. And after we've done so, Well, we've picked 3 cards from our deck. So we're left with 49, and we just choose the last 2. And then what we got to do is just make sure that we haven't somehow included one of these other arrangements in there. And there's actually 2 here that this could possibly contain. We have a 4 of a kind, and we have a full house. Now, if I chose, if I get a 3 of a kind, and I am in this, this setting where I get a full house, I have these 3 chosen, and then 2 sort of come about. So every single 3 of a kind relates to exactly 1 full house. However, with 4 of a kind, which I might actually fall into, if I chose these 3 cards, there was 4 different ways for me to do it. So I actually overcount my 4 of a kinds, if I'm not mistaken.
Ryan, I think the full house number might not be right here.
Oh, which part? Just like the numerical value, or just subtracting it
How
out?
much do you subtract?
Because each full house, each 3 of a kind is paired with 12, or at least 12
Oh,
full houses.
oh, I see.
It's paired with 12 times 6,
Yeah,
which is
72.
72.
Yes.
Let me say this the easiest thing.
Right. So,
Select 3 from the suit there.
so this is, yeah, full houses. Well, this is going to get, no,
You did, all the full houses are counted by the first quantity.
yes.
Right.
And I don't think we overcount them at all, actually.
No, maybe that is.
No, I think this is right. Because, yeah, if we got just 3,
Yeah, that first triple binomial coefficient includes every full house, right?
yeah, so if I got this as my triple, then this is going to, yeah, this is going to get every full house that includes this triple.
Yeah, and for true for every. I think that's right.
Right, so there's, if you choose the 3 that match, that corresponds to multiple full houses, but the full house count includes like many full houses.
Exactly.
Yes.
Exactly.
Okay.
This is going to take care of all of those ones. Absolutely. But the 4 of a kind, we actually do have to be careful, because we've picked the 3. I should have left it there, but we picked the 3 cards, and then we might add the 4th. But there were 4 ways we could have actually done that. So we actually.
It's not determined by the 4th suit? Because you have 3 suits already, so you can only add a 4th in one way.
You can. I think the problem is, let's see.
I believe you.
I'm trying to, yeah, well, I'm teaching you. I'm trying to teach you, Van. Let me teach you. Yeah, let's go, let me redraw this bad boy. So we have a 3 of spades, we have a 3 of hearts, and we have a 3 of diamonds. Now, this guy right here, the 624 is going to calculate when I have all, like, 4 3s. I'm going to get all of the different ways I could have gotten my 4 3s. Now let's see what's happening here. I decide,
Yeah.
We think you're okay, Ryan.
this right?
Yeah, because
Yeah.
here you're sort of like arbitrarily saying 3 are gonna be
Yeah.
your.
3 are my triple, and then I tack on a new one, and I've sort of just overcounted this thing. Okay.
There's a way to solve this without having to subtract.
Yes.
Were you about to do that as well?
I was.
Okay, good.
Yes, I wanted to, yeah,
We'll want to see both.
absolutely. I wanted to do a few of these with a subtraction, to show how we can. But yeah, let's for instance, let's do this 3 of a kind without subtraction. We can just use multiplication principle here. So let's, again, we're going to choose the rank, and then choose the 3 of that rank. And now it's not that bad. What we're going to do is, well, I chose these 3 cards, but I don't want to get this 4th card again. Or I'm sorry, I don't want to get the same card of the same rank. So let's choose from the 40. Oh gosh, yeah, 49 remaining. Make sure I'm doing this right.
48, choose 1.
Yes, thank you. Thank you. Yes, yes. Because we once we've picked our 3, we drop that 4th card from our discussion, because if we leave it in, we might get a 4 of a kind. So we get 48, choose 1. But now we want to watch out for getting a full house, because if this card, or yeah, if we get another card of whatever rank this is, then we're in that paradigm. So we just lower our count by 4 again, and we have 44 choices, and we choose 1 card. And these 2 happen to be equal.
Can I suggest one more count?
Please.
So what if in the 49 choose 1 step? I mean, just, no, don't worry.
Oh, I just wanted to clean it up. The A just looked kind of gross.
So what if, so you pick your 3 of a kind, in 13 choose 1, and then 4 choose 3.
Mm-hmm.
And then I'm gonna pick 2 more ranks from the remaining 12 ranks.
Mm-hmm.
Right, so 12 choose 2 is my next term.
Mm-hmm.
I want my next 2 cards to be of different ranks from each other and from the one I've selected.
Right, so let's do that. Yes.
12.
Yes, we choose 2 ranks.
And then
Awesome.
I need 2 4s here, right? From each of those 2 remaining ranks. I need
Absolutely.
to pick 1 card.
Absolutely.
And so I'm also claiming that 12 choose 2, 4 choose 2, 4 choose 1, 4 choose 1 equals those other binomial, right? That's
That was easy.
that one seems pretty
what's so cool
good.
about these is the
Yeah.
variety, right? Like these all work out.
Absolutely.
So, I think it's not equal though. There's
So something's
an
fishy.
extra factor of 1/2, and I think the issue is that in the second line, 48 choose 1 and 44 choose 1,
You
you're
put
imposing
an
an
imposed
order.
in order, yeah.
I imposed an order.
Yeah.
choose-
So
Yeah, I
let's
think-
include a 1/2.
By 1/2.
Yeah.
Oh, yes. Yes.
Yeah,
Thank
that's
you.
what the 12 choose 2 avoids doing, right? You chose
Exactly.
and you didn't give them a first.
Precisely. So yeah, just for viewers at home, with this second way, we chose our rank, chose 3 cards from that rank, and then we chose another card that's not of that rank. We choose a 5th card that's not of either rank to avoid a full house, but it actually didn't matter the order that we chose these, so we got to divide by 2. So for that, I honestly, I don't like this one very much. So I like these 2 solutions the best. So what else do we have left?
All right, Ryan, one more.
Yeah,
I just
please.
What if we choose the 3 suits in advance?
Okay,
The 3
3
ranks in advance, right? One of which
Okay.
would be,
so are we gonna, okay,
choose 3.
13 choose 3s,
Now I've decided my ranks.
boom,
One of those
Decided my
ranks
ranks.
would be the triplet rank,
okay.
3 choose 1.
which is 1. And then I guess a 4 choose 3 to decide the 3 in that.
Absolutely.
rank. And then is it just 4 choose 1, 4 choose 1?
Yeah.
Of those
I
ranks?
think so. Yes, because the other ones, we only have one of both of them, so.
We need to pick them though.
But yeah, 4 choose 1, 4 choose 1, right? That picks.
That picks their suits, but we need a 10 choose 2.
No, but the 13 choose 3 was, I set aside which 3 ranks are my.
Oh, yeah.
right?
Oh, I'm with you now.
Yeah,
And this would avoid a full house as well, right? Because I've said
Yes.
3, but not 2.
exactly.
That should
We,
be equal.
I think we
We don't know
should,
too many
we can,
binomial identities.
yeah, we can check, maybe. I think you're right.
You don't want to kill the 4s.
Yeah, if you're canceling, I think the 13 choose 1, 12 choose 2, and 13 choose 3.
Yeah, that's
They fit together nicely.
yeah, that's all we need to show is 13 choose 3, 3 choose 1, 13 choose 1, 12 choose 2. Is that right?
Yeah, I believe it.
Yeah.
Yeah, that's 13 times 12 times 11 over 2 on the top, and then 13 times
Perfect.
12 times 11
Perfect.
over 6.
Sorry, Ryan. This is too.
But most importantly,
Oh yeah, what?
there's what matters here, guys, is that there's 54,912 of these. And just to add some space, I'm gonna erase my naughty count and put this guy there. So I'm just gonna do that. Just wanna leave it there.
What's the most annoying way we could compute this? Like 52 choose 5 minus.
Everything that has at least 4 ranks.
No.
Oh, that's good. I
Okay.
think that will come up something like that later.
Okay. So now, see, we got 3 of a kind. Next is 2 pair. We're really close. We're not going to do high card.
But it's an easy subtraction principle.
No, this is my show.
No, you've done it.
No, I'm just kidding. I'm teasing. I'm sorry. Okay. 2 pair. How are we going to do 2 pair? Let's do multiplication first. Why not? So we're going to first choose our pair. Let's do that. So from the 13 ranks, I'm gonna choose 2. And from the first, there's 4 suits, and I'm gonna choose 2 of those suits. Oh, I think I didn't say this at the beginning, and I like to just be disorienting. This is the capstone problem.
Yeah, the capstone problem.
In case you weren't aware, we've chosen the ranks of our first pair, and then we choose the rank of our second pair, and we just choose another card for that last bit. And so, what did I do?
You're not choosing suits in the middle?
Wait.
Yeah, that was 2, or no, that was 2 of a rank.
Yes.
Right?
Yeah. We chose our ranks, and then this chooses our suits. I'm bad with words. And then
Feels 2.5 hours in.
absolutely, 52 minus 8. Choose 1. We choose 1 more card. Doesn't matter which one it was, so long as it wasn't from our chosen pair. That is the important part here.
So Ryan, did you write 52 minus 8 because you're not able to compute 52 minus 8?
No, Corey, it's a really easy subtraction. No, I definitely, my brain is blanking, yes, absolutely.
Yeah. Right? Yeah. That step you could also have done by like
Yeah, my brain is
11 choose 1
firing.
times 4, which is this obviously the same as 44.
You can color it two different ways.
That's nice actually. Yeah, there's more.
Absolutely.
going on. Yeah.
Okay, but let's do a subtraction.
And Ryan, actually, this one,
Yeah.
if we had counted in a different way,
Mm-hmm.
we would have also done subtraction. We could have thrown out 3, even 4 of a kind could have occurred, right?
Yeah. Oh, yeah. We can. Yeah. Honestly, it depends on how we wanted to count it.
No, not 2 pair.
If we decide in advance, like, okay, we're gonna have 2 different, then I think the only thing we have to worry about is a full house.
Yeah, you're right. You couldn't get 4 of a kind if you chose that, right?
Yeah.
I see.
So long as we make sure to determine our pair at the beginning. But yeah, there's many ways to count this. I think that should be, I don't know, maybe not clear, but that is like sort of the crux of this discrete math, and that's kind of what makes it beautiful is, yeah, we can write all these symbols and maybe they look kind of crazy and maybe a little different, but they somehow count the same thing.
I I mean, it's cool.
It's
The
wonderful.
The subtraction one, the other, but it's totally not obvious those should be equal.
No, but if you, yeah, but it's wonderful, and it's just, I don't know, proof of concept, I suppose. For this 2 pair, I'm just going to leave it there because I'm going to just sort of get to our next ones. Did I tell us what it is? How many 2 pairs are there? There's a lot. Maybe not a lot there, but it's bigger than what we just had. Okay, wonderful. 123,000. Okay, we're getting big. Okay, and I think we have 2 more. Yeah. Okay. We have 1 pair. Okay. So for 1 pair, let's choose our rank.
By 1 pair, do you just mean like high card? Is that it?
1 pair, like two aces, 2 threes. No problem. No, thank you for asking. Yeah, 1 pair. So 1 rank shows up twice in my hand. So we choose our suit, or sorry, choose our rank, and then we choose the suits that pop up for that rank we picked. Sorry, I never use the word rank when describing cards, so saying it many times, it's a little difficult. It's beginning to rankle a lot. Okay, I choose my pair. Now I want to make sure the last 3 cards. Let's choose them. 13 12. Choose 3. There we are. We have 12 ranks remaining because I don't want to think about this pair anymore, and I choose 3 from there. And for each of those, doesn't
I
matter.
don't guarantee you don't get another pair, right?
Yes.
Definitely 3 different ranks.
Yes. Yeah. This guarantees we don't get another pair. We've chosen in advance 3 different ranks. And so for each of those, we just choose our suit.
Nice.
Cool. And that is equal to 1,098,240. Cool. Almost half of all possible hands. Or 1 pair. Let's just, because somebody said it, so let's actually do it. Let's do number of jacks or better.
Oh, okay.
Because if you've ever played a machine, you know that if you get 1 pair, well, I mean, I guess this sort of maybe explains why just getting a pair on a machine is not enough to actually get you money, because you actually have a pretty good chance of getting a pair. What about if we want to just go jacks or better?
Does that mean a pair of
A
jacks?
pair of jacks, exactly. A pair of jacks. So in this case, we actually only have 4 ranks to choose from. We could be jack, queen, king, or ace. So let's choose our rank. This feels wrong.
Yeah.
But yeah, let's do it anyway. Oh wait, no.
Right,
I think that's right. It's
Rank.
just suspicious
Yes.
that it's the same.
not suit.
It's rank, not
Yes.
suit, but yeah.
And then from there we choose our suits. Right. And then, yeah, I think the key is that this part is kind of the bigger contributor. So 12, and then I think we do everything about the same. We have 12 different ranks that we haven't picked from. We're going to choose 3 cards. And from each of those, we're going to choose our suit. And I didn't actually calculate this one in advance.
So, Ryan, I think 12 choose 3.
Is that
Should
wrong?
not be 12 suits anymore because. No, oh wait.
Yeah.
No,
We
no,
can't,
wait.
we can't get a pair.
You can't, you're not,
So
you won't.
Mhm.
Okay, never
Jack,
mind. Yeah,
Jack,
you can have two jacks and a king. That's,
Yeah,
okay.
yeah. So in this case, it actually, yeah, it's kind of weird. We have 4 right here, and then we're left with 12. But the reason why is at this beginning, we're forced into taking one of these 4 ranks. Like we have to take that. But we know that the last 3 cards that we're gonna get don't give us anything good. They're not gonna add up to a 3 of a kind, 4 of a kind, none of that. So it can be any card, any rank, and then for each of those, we have its suit. And I don't actually know what this is, but
4/13ths of that,
exactly.
which is about a third.
Okay, what's
Which
the number
is-
above? 1,
Yeah, so
Like 300,000
What-
and change.
yeah, what's nice, what's nice about the difference between the number of 1 pairs and the number of jacks or better is sort of just an added little bonus here, is that the only thing different is there's this 13 choose 1 and this 4 choose 1. Everything else has stayed the same. And what's nice, we've already discussed this, 4 choose 1, that's 4, 13 choose 1, that's 13. So jacks or better is just 4 13s of what we had originally, which my crowd.
33,792.20.
Wait,
7, 9, 2, 300.
337,920.
oh, wait. 1, 2, oh,
Is it the right?
yes, for some reason I forgot this is a million.
A million.
Yes,
Round.
yes. There we go. And as if what's really nice to see too, just to, I guess again, if you do gamble, guilty, this is less, I'm sorry, there's still more jacks or better than anything that we've seen thus far. Like 2 pair, 3 of a kind, I'll just look at those.
Would queens or higher be less? Is
Yes.
that's why they cut it off there?
Oh, I see what you're asking. Oh, I actually don't know.
It is not.
It's probably not. I think.
It would still be like more common?
I
I
feel like.
Wouldn't be enough. Okay.
Yeah. No, that's funny. I don't think that's necessarily cut off, but I guess it's good enough. I think the idea was just it being the face cards. Sort of
Sure.
just makes the most sense, and it's a small pool. But then, okay, so we're about finished, but we forgot one hand. What if you lose? What if you got nothing? So let's count that. I'm gonna just,
That directly for us?
I'm going to do it right here, in this space, right here. It's going to be 2, 5. Oh. So it's, no, I don't think you can. Oh, count it directly. I was doing a joke, but yeah, I think you could count it directly. Let's do it. So number of, how do we want to say? Oh, high cards. Which, let me be clear. Let me be clear. Number of high card hands, you could win with a high card hand. You could bluff your way to a victory easily because
Well, it's likely that someone else has a high card hand.
You could have the high, I mean, if you.
it
have
is
ace
likely.
high,
We'll see that in a second. Don't spoil it. Don't spoil it, man. We're not there yet. We haven't figured out the count. Okay, so the high card, let's count it directly. Why not? So we're going to choose 13 different ranks, or 5 different ranks. Okay, there's a problem here that I'm already seeing. What if we end up with a straight
Or a flush.
or a flush?
I think we can just.
Let's just full steam ahead. Okay, pick your 5 cards.
Distinct rates, right? That'll be distinct.
Yes, these are 5. Yeah, we're picking 5 distinct ranks from all 13 possible, and for each of those, we can just pick a suit. So let me write it like that. I think it's nice flair and it's the truth. 4 choose 1 to the 5th. Okay, so that's all high card hands. Is that it?
No duplicate.
With no duplicate. Thank you. I was looking for the stipulation because this is definitely not all possible hands. We have no duplication. That's what this fella right here is guaranteeing for us. And now, but we could have definitely gotten a straight. We
Or a straight flush.
could have gone a flush or a straight flush or a royal flush.
Advanced things to fix this one.
No, because these are already partitioned.
We've already partitioned it, so we're okay.
Oh, they're
That's what we call foreshadowing. This is wonderful. But let's subtract things. We got the royal flush. We got the straight flush. We got the flush.
Oh, I see.
And this is okay because in each of these we've already subtracted our the parts that are going to be bad. We're not going to subtract. We're not subtracting too much at any point. What else? We got to watch out for straights. Okay, minus these. Watch those. And just we could have also, just to sort of, what I wanted to do here, but with all the space that I have on this board, would have been really annoying. What we could have totally also done, just start with 52, choose 5, and just subtract everything that we've already done. And you'll get all of the other hands, which, again, just to sort of just finish this off, because how many? Are there more high card hands than other hands? Yeah, of course. Let's hope. It's actually, compared with one pair, it's, you could say relatively not that much, but compared to everything else, it's actually more than half. It's 1,302,540. So yeah, comparing that to your all possible hands, the way we've set up our rules is actually kind of nice, I guess, because it's not much more, but it's just enough. It's just enough to be out of your favor.
Do you think, Ryan, it can be computed without subtraction?
Yeah, I think so. I think you could. I think if you,
I'm wondering if, when you choose this, so you chose 5 ranks, you can somehow mix ranks and suits to avoid flushes and straights. I don't know.
right. Could you, oh gosh, I was gonna say, could you, after we choose our first suit, we have at least one that's a different suit?
Yeah, but
That's,
maybe end up in inclusion exclusion.
yeah, exactly.
You can sort of do, we look at, sometimes we look at, strings without consecutive, then,
We're actually at the end of this section, by the way, viewers at home and viewers over here. We're just sort of chit-chatting now, trying to figure this out.
Ryan, is this the end?
This is the end. We're actually right there, I think. Let me just. This is the end of the first 6 hours. Oh, it's not the end. Oh, I kind of want
If you
to.
want to, by all means.
No, I think we're good actually. No, yeah, let's do them. Let's do these last 2. I'm gonna do one of them. We're okay.
Oh, right.
Multi-sets or whatever.
That can be, I can
We're
do
fine.
that later.
When do you ever have a multi-set?
Often.
We can
I've never seen one.
look at multi-sets.
There's really multi-sets.
Oh yeah. Well, I liked this problem. I just kind of wanted to stay with that. But yes, the key here is don't gamble. Or if you do, be good at it.
You gotta play against people, right?
Yeah, exactly. Play against people, because then you can win with a bad hand, which, as we can see here, is most of the hands. But let's finish off with another card game, because, some mathematicians gamble. Others go to Friday Night Magic, or Saturday Night Magic? The other one. One of those.
the inventor of magic was a mathematician.
I believe that. I believe that. I mean, honestly, maybe they're not with all of the boycotting happening. Wizards of the Coast is messing up right now. It's grand. It's wild to see, and people are mad.
Is that the same as the magic? Does Wizards of the Coast own magic as well as Dungeons and Dragons?
Yes.
That's we need antitrust.
Yes.
I know, they have too much.
But
Too much, all the cool fantasy stuff should not be in the way.
I know. Damn you, Hasbro. That's my one cuss word of the day. Got him. Okay. So Magic the Gathering, it's a card game. You face off against another person. You both have 40 card decks. And the thing is, you use land, it's mana. This is the way that you're able to actually use your other cards. They cost a certain amount of mana. So part of playing Magic the Gathering, and most card games maybe most card games, kind of build their system off of this. You've ever played the Pokemon trading card game? I haven't. I just used to get the cards. They were kind of cute, right? Yeah, I have a Charmander in my bedroom. It's really cool. It's not a very good card, and you can get it easily, but I like it because it's a nice drawing.
Shiny?
No, but my brother does have a shiny Charizard. That is pretty cool. But anyway, so if you start the game off, and this was not a rule at the beginning of the inception of Magic, and now it's even a lot more liberal, but if you end up drawing your initial hand, and you have 7 cards, or 7 lands, or no lands, which are both bad positions to be because you need lands to do things, but if you only have lands, you can't do anything. So you're able to mulligan, which is just redraw your hand, and you lose a card, but you redraw your hand. That doesn't matter in this scenario. So we might want to ask, well, what's the probability that a player can actually mulligan? And using addition and subtraction, this isn't the worst. Let's see. So, and we've only had I think this is maybe the second probability question. So let's be careful here. So when we're doing probability, let's just, what we care about is sort of our whole universe. What is the count of our universe? In this case, we can draw 7 cards from a 40 card deck, and it does not matter the order of those cards. So there's 40, choose 7 hands. And of those, well, if I only get land, well, I had 17 lands in my deck, and I chose 7 of them. And if there are 17 lands, there are 23 non-lands, and I also, in this case, I chose 7 of them. If this happens, this actually ends up being our probability, because these are our only ways of doing it. I choose no lands, I choose only lands, I choose a hand. So we get our probability, which is approximately, anybody have a guess? Incredibly small. Yes. If in the original ruling of mulligans, it was incredibly rare to actually achieve a mulligan. Well,
Like a 70th?
yeah. Like a 70th chance. And gonna end my time here, 2 minutes over, whatever, with just sort of saying last that you can mulligan if you have less than that many lands in your hand. So your chance of mulliganing is actually 100% now. Wonderful. If you want.
Can I ask a follow-up then?
Please.
So back in those battle days,
Mm-hmm.
you could mulligan again.
Ah, yes, at six cards.
How would you compute the probability of that? Do you know? I'm assuming you discard and reshuffle.
Yeah.
right? And then you redraw, but you only draw 6.
Yes.
And so it would just, you'd have 6s replacing the 7s everywhere,
Mm-hmm.
right?
And
Oh, the penalty is not just that you don't lose your turn, but you get
No,
on,
I think.
you lose a
I
card.
think you lose.
You draw one less card.
In fact, I think that was the original rule as well.
Mm-hmm.
But
oh,
then,
losing a turn.
yes, almost certainly, right?
Yeah. Well, you.
It depends.
Well, I mean, if it's like Yu-Gi-Oh, where most things are over.
No,
Well,
not quite.
if we want to, yeah. I mean, would it not just be multiplying those probabilities?
Multiply the
Yeah.
probability.
Okay. Yeah, which would make it even smaller to actually be able to do any of that.
But individually, the probability that in drawing 6, you'd have all land or not should be higher,
Mm,
I think.
Yeah, because it's really high,
Choose
since you
6
have
plus-
one card.
Right,
Yeah.
So you think
yes.
it would just.
yes.
Yeah.
Yes.
It feels like.
Yeah.
Well, I guess there would be an optimization. if it was-
Yes, because this bad boy is getting smaller as
Oh, yeah,
these are
but
getting
you-
smaller.
In some sense, you can think of drawing 7 as you drew 6 with none, and then an additional condition was.
Yeah.
Right. Okay. I'm ready to go on my 12-hour break. Okay.
Well,
I'm
why don't we
gonna.
take a couple minutes
Yeah. Let's take a
break
couple minute
anyway,
break.
get set up.
Thank you all for attending.